A couple of notes that I've been sort of in conversations with you all and through seeing some of the results of the quiz and just office hours and stuff. I wanted to clarify a couple things that have been coming up. So one is when we're using Maple, I think the best way to use Maple is to use it as a symbolic solver. So by that I mean, like, if I give you a number 0.13 or 1.3 or 295 or something, you probably don't want to enter that number into Maple directly because it's going to start propagating through with numerical precision error and you get these really long, weird looking numbers. So really what you want to do is have symbolic values for everything that you're putting in there. Take the symbolic result and then use it in Ease or Python where you can provide a numerical value that goes with that. All right, I think it's just cleaner. It's an easier way to understand the results. So that would be first recommendation for Maple. Second recommendation is I think a lot of people were thinking, okay, you go through, you're using Maple to come up with the general solution and then the boundary condition equations, and then you have to somehow explicitly solve for C1 and C2 in these problems. If you're using Ease, you don't have to explicitly solve, right? You can just, as long as you have the right number of equations and the right number of unknowns, it should be okay, right? So if you're in a situation where you're going to use Ease, or maybe you're doing an iterative solution, which we'll get to later, you can use Maple just to get to the point where you have the right number of equations and the right number of unknowns, and then go from there. I think, in fact, if you tried to solve explicitly on this homework, you probably ran into some issues with Maple. Okay, so that might have been a little painful. But again, you don't need to do that the full way. Let's see, any questions on that or Maple in general? Like, I know that this is probably the first time you're all using Maple, so it's a bit of a battle to know what you're doing. But the best thing to do is just to try and fail and try again. So I think you're right at that point now. So any questions on Maple that we can talk through? Nothing as a group? Okay. As more stuff comes up, I think I'll try to mention it, but there's a learning curve, right? But I think one of the important things you're going to come out of this class with is just being able to do problems using the tools that are available to you, not just doing problems by hand and leaving it at that. Okay. Last thing was, I think we're still not quite clear on boundary conditions and how to enforce them. So I just wanted to recap quickly when you're enforcing boundary conditions, what it actually means and like what you're doing. So let's just do a really quick example. Let's say you go through, let's say you have some plane wall, right, and you're conducting in the x direction. And let's just make up some boundary conditions. Let's say over here you have some specified temperature Tc. And on this side, you have a specified heat flux, which we'll call Q dot double prime, right? And that's going to be times the area that it's hitting. So that would be, I guess, we'll call that AS. So those are our boundary conditions. If you go through this plane wall, no generation or anything, you'd end up with the ODE, which is d squared t dx squared is equal to 0, right? That's your governing ODE in temperature for this problem. If you solve that ODE for the general solution, you end up with t as a function of x is equal to, well, c1x plus c2, right? This is the easiest solution. What it means to enforce the boundary condition is you need to take this temperature general solution that you've come up with and relate it somehow to those equations, right? The boundary conditions that you have. So, for example, if I look at the TC side, how do I enforce that boundary condition? I'm just saying this stuff on the right-hand side, this temperature general solution, has to be equal to Tc at this x position. So let's say we'll call this L, right? So I'm just saying Tc has to equal C1 times L plus C2. That's enforcing the boundary condition on the right-hand side. On the left-hand side, and I think this is where people are confused, this is a flux boundary condition. In the homework, you have a resistance network boundary condition, right? Or you should have. So if we try to enforce this, what we need to say is Q dot double prime AS is equal to what that's valid in the domain. It's conduction in the domain that's governed by Fourier's law. So Q dot double prime AS, we're given, say, Q dot double prime, we can calculate AS, has to be equal to Fourier's law minus K times AC times dt dx. In this example, if it's a plane wall, right, AS is equal to AC. So that goes away. And then when it comes to enforcing this boundary condition, again, what we're doing is we're saying I have a general solution for temperature here. I can plug that general solution for temperature in any place I see T. So I need to take the derivative of that general solution in order to enforce this. And this would end up being q dot double prime is equal to minus k d dx of c1 times x plus c2. Right? All of this has to be evaluated at x equals 0. So if I go through this, sorry, I ran out of room, I guess I'd end up with q dot double prime is equal to minus k times c1, right? Because you just take the derivative, evaluate this expression at x equals 0, nothing changes. And this gives me c1 is equal to minus q dot double prime over k. Right? And now I've solved my system of equations. So that's just to recap what it means to enforce boundary conditions. Now when we get in, like what we had in the homework, you get something that's more complicated than this on the left-hand side, and you have to be a little bit more creative about it. But ultimately, you're just trying to come up with equations that match on outside the domain versus inside the domain.